Hello everyone, today our Group 33 will present our research that is knowledge distillation for code generation in security environment. Well, this proposes an innovative framework to address the dual challenges faced by some state-owned enterprises. Today, over 60% of the code written by some software developers is AI generated. However, security-sensitive organizations like some state-owned enterprises, they face some critical challenges. They must run the models within physically isolated internet environments with no cloud connectivity and restricted internet environments, so that the traditional large language models cannot deployment with the developer's personal laptop. Well, this is the problem. To solve the dual problems, we use the knowledge distillations, that the large parameter teacher model passing the knowledge to the small parameter student model. It has three core values. The first is model compression. The second is it can perceive the interface performance. Well, the third core values it can support in internet development. Well, let's talk something about the related work in knowledge distillations. Well, the foundational framework of knowledge distillation was proposed by Hinton in 2015. After years of development, current knowledge distillations are mainly become three parts. The first is the response-based distillation, which is the Hinton's method. The second is the feature-based distillation, which transports deeper knowledge by aligning the middle layer of teacher and student models using the MSE laws to match the different states. The third is the relation-based distillations. Well, these preserve the structured relationship among data samples.
We use the Queen 2.5 coder 1.5b as the teacher for its strong Python understanding, patterned on the codex glue code-to-docstring dataset to specialize it in code comprehension and generation. The student model, Queen 1.5 0.5b, was trained to 20 transformer layers, reducing latency while keeping enough capacity to learn from the teacher. Both models were trained with data in Queen prompt format, where each sample contains a code snippet and an instruction, mirroring real code tasks. Distillation combined two strategies. Logic-based, the student aligns its output distribution with the teacher's soft projection, using soft cross entropy loss. Feature-based, the student's hidden states are mapped to match the teacher's projection layers, help it internalize the teacher's reasoning. This dual approach transfers both surface knowledge and deep representation, producing a smaller model with near-teacher performance at a fraction of the cost.
Now it's my turn to introduce the part of performance evaluation. First, we test the impact of temperature on logic-based distillation. This table shows that the model trained with the temperature of 4 achieved the best performance in both blue and rouge scores. Next, we test the impact of beta on feature-based distillation. The results indicate that the model performance initially increases and then decreases as beta changes, with the optimal performance achieved at beta equal 2. Performance degrades at beta equal 5, suggesting that an excessively high weight for the feature loss may interfere with the student model's learning of the primary task. Finally, we test the comparison of different training strategies. The logic-based distilled model achieves a BLUE score 2.6% higher than the non-distilled student, validating the effectiveness of knowledge distillation. Subsequently, we reduced the training set size to 2,500 samples and retrained the 3 models. The results indicates that the teacher's knowledge becomes more critical with limited data, allowing the student to learn from the teacher's guidance on unseen samples, thereby achieve better generalization ability. That's all. Thank you.